Alright, we're back with 6.1 problem number 8. I've already done half of it. As a matter of fact, I recorded the whole thing. But when I looked back at my camera, it had stopped recording for some reason, so I have to redo the second half. Alright, so anyways, when we left, we were talking about the radius here, and how could we write the radius of this disk that will work for every single disk. And we look and we'll notice that this edge is governed by this circular equation, and that we will always be x as governed by that circular equation. X will always be the radius, right? The radius of our disk will always be x. And so now we can find our small chunk of volume. We call that dV. And that's going to equal the surface area of a circle, which is pi r squared, times the width, right? Extruding it into 3 dimensions times by the infinitesimal dy. So the next step is going to be if we know that r is equal to x, right, as we described earlier, then I can actually rewrite r in here as x squared. And you can use your circular equation to solve for x, because remember that circular equation is governing everything in this problem. So we solve for x and we find that it's equal to the square root of 225 minus y squared. And so we can now plug that into our dV, our small chunk of volume formula. So what is the square root of 225 minus y squared equal to? Well, the squared here just gets rid of the square root, and we're left with 225 minus y squared dy. Alright, so the next step here is we're going to integrate both sides from our bounds. So the integral of dV the integral of 1 dV is actually just v, right? Just like the integral of 1 dx is actually just x. So what we end up with is a formula that says that v equals the integral of pi times 225 minus y squared with respect to y. And our boundaries are from negative 15 to minus 5. Alright, so I'm going to go ahead and make some room now. Hopefully the last video helped you visualize how to work these problems, because drawing them is crucially important to understanding them. And although there are formulas on your cheat sheet, if you don't know which one to use, by setting up the problem visually, you'll probably end up using the formula incorrectly anyhow. So I always recommend drawing at least a 2-dimensional figure and then a 3D slice, whether that's a washer or a shell or whatever other method you're using. It's always good to draw it. Alright, so here we can take out the pi. And we just end up with 225 minus y squared dy with a pi on the outside. So now we'll just do the reverse power rule and find the derivative, or the integral, which is 225y minus y cubed over 3 times pi equals volume. Oh, I'm sorry, we're evaluating this from minus 15 to minus 5. And so to do that, we're going to keep the pi on the outside. And then we're going to plug in our upper bound and then our lower bound. So 225 times minus 5 minus 5 to the 3 over 3. Just plugging in minus 5 wherever there's a y. And then subtracting when we plug in minus 15. 225 times minus 15. Alright, so here's the thing. This video is more about setting up and solving the problem, and I already solved it once in the last video and it stopped recording on me. Go ahead and just plug this into like Symbolab or something like that, because I really don't feel like doing it again. There's just a lot of rationalizing fractions. Anyways, the answer for me was 3665 centimeters cubed. And it asked us to round to the nearest centimeter. But hopefully this video will help you set up the integral, because solving it is something that we already kind of know how to do. But setting it up is usually the tricky part of this problem. So anyways, I hope this was helpful, and I'll see you next video.